Today we're going to look at inverse functions. An inverse function is denoted with the little -1 that you see here. So we just say it's the inverse function, and it actually reverses the original function of f of x in that it actually switches the input and the outputs, so that if I was actually to do a group composition in either way, the original function and the inverse function will always result in a linear line called x of x. Or if you look at it another way, if we were to look at a table of values, all your inputs of being 1, 2, and 3 now become your outputs, and their outputs now become their inputs. Now, part of the properties of having an inverse, or having an existence of an inverse, is that it will only exist if it's 1 to 1, which results in having the domain becoming the range of the inverse function, and the range becoming the domain of the inverse function. So let's look at an example on how to find an inverse of a function. The original function we're going to look at here is the square root of 4 minus x, which we can see visually has a domain where x has to be less than or equal to 4 for all real numbers, and that y has to be greater than or equal to 0 for all real numbers. We can look at a little table of values for this, and we can see that we've got some values here of 4 and 0, 3 and 1, 0 and 2, and -5 and 3. Those are a couple of the points that exist on this actual graph. So, how do we find the inverse? Well, like I said above, you actually ultimately switch the x and the y values in the equation, and then you re-isolate for the function. Now, keep in mind too, it has to be 1 to 1, so therefore the domain of this function will become the range of the new function, and the range of this one will become the domain of the new function. So, if we algebraically start looking at what we have to start off with, we can see that if we just switch the x and y initially in our equation, just so we have an idea of what the equation is going to look like, we can then manipulate both sides of the equation to kind of isolate for what our y would be if we were to write it in terms of function notation in terms of y. So we would then have 4 minus x squared. Now, in order to do this, we have to keep in mind the restrictions of the domain and the range. This is a full parabola. It starts at 4 and then it goes down. So we have to make sure that we are actually showcasing just the relevant domain and range, given that this is just the positive square root, not the positive and negative square root. So, if we were to look at our table of values and make sure that it works, our new function will have the exact opposite operations. Switching around, we'd have 4, 3, 0, -5, and we would have the points on the graph that correspond. Let's put it there and there. So it's something to the effect of, that one's slightly off. There we go. Something to the effect of that. Now again, it also, one of the nice properties of this, it does reflect over the line y equals x. As you can see, like so. So now we're going to consider the derivative of the inverse. What we're going to look at right now is a couple of pieces of notation, and then we're going to look at an example of why this is useful. If f is differentiable and 1 to 1, therefore there's an inverse of, we'll call it g of x, which is just f inverse of x. And if b belongs to the domain of g of x, so we know that if it's in the domain of g of x, then that means it has to be in the range of f of x because it's 1 to 1. And if the derivative of f prime of g of x is not equal to 0, then it exists, and we can actually use this little fact right here, which is ultimately the chain rule. And it's utilizing the fact that the original function and the other function as a composition, the inverse function as a composition, is equal to x. So if we were to actually rearrange this, we can just see this is ultimately just the chain rule. If we were to take the derivative of both sides of the equation when we had a chain rule, and we know that their product, or their composition I should say, is actually equal to the x, the derivative of x is 1. So that is why this is holding true. So here's an example of what if we can't find the inverse. we're going to look at the function x plus e to the x, and we want to calculate the derivative of the inverse, g prime at 1, where g is your inverse function. We're going to use this fact here that we just talked about to help us do so, without actually trying to figure out what the inverse is. If we tried to figure out what the inverse was, we would then switch these like so. But we don't necessarily have the tools to isolate for y. So it's not as straightforward as we were hoping for. What we can do, though, is figure out what the derivative of f is, which we now know is this from our last class. And we also can figure out what f of x is going to have to equal to 1. If we keep in mind that our g of x function, our x and our y, x is going to have to be 1 for our g of x. And in our f of x, that just means that our x and our y, we're looking for when y is equal to 1. So if we need f of x to equal to 1, then we can basically look at this to determine that if x was equal to 0, 0 plus e to the 0, which is just 1, that would work. So there's one of our particular solutions. So now if I want to look at the inverse function, which I don't actually know what it is, but if I want to look at the inverse function, I can then fill in some information that I already know about this. Now in this case, I'm looking for it when b is equal to 1. So the derivative of our inverse function at 1 is going to be 1 over our derivative function here with g of 1 plugged in. G of 1 is 0. So I'm actually looking at the derivative of this when 0 is plugged in. So no need to calculate any of the derivatives for the inverse. We don't have to worry about trying to figure out what the inverse is. But now I can look at this and say, okay, here's my derivative. So g prime of 1, the derivative of 1 at 1, of 1 over 1 plus e to the 0. So as a result, 1 over 1 plus 1, so 2. So you get 1/2. So I didn't have to find the inverse function. I didn't explicitly have to find it because we don't really have the tools to write it in terms of y is equal to something. I didn't have to find the derivative of it, but I used the fact that the inverse and the original, their coordinates, they just switch when I move them over, and I use the formula to figure out just by using the derivative of the original function.